All right, let's jump right into this explainer. If you've ever stared at a computer science exam paper and felt a cold sweat form when asked to convert floating point numbers, you are absolutely in the right place. Today, we're completely demystifying one of the trickiest concepts in data representation, handling negative mantissas and both positive and negative exponents. By the time we wrap up, you'll have a foolproof mental study guide so you can tackle these conversions with total confidence. Here's the game plan for today. First, the floating point challenge. Then our two's complement cheat sheet, moving right with positive exponents, moving left with negative exponents, and finally, common exam pitfalls. Part 1. The Floating Point Challenge. Let's start by identifying the main threat you'll face on the battlefield of your exam paper. When you're staring at floating point binary numbers, it just looks like a massive jumble of ones and zeros, right? But there's one specific signal you literally need to train your brain to scan for immediately. If you spot a leading 1 in your mantissa or your exponent, you're dealing with a negative value. That means immediate conversion is required. If that very first bit on the far left is a 1, alarm bells should be ringing in your head. It means the number is hiding its true decimal value and we've got to decode it. Moving on to part 2. The two's complement cheat sheet. To defeat those negative values, you need your primary weapon. And this perfectly illustrates the incredibly simple two-step process you have to burn into your memory for exam day. Step 1 is one's complement, which is really just a fancy way of saying flip every single bit. Zeros become ones, ones become zeros. Easy enough. Then step 2 is just adding a binary 1 to your flipped result. That's the whole shebang. Flip the bits, add 1. Remember that, and you've basically won half the battle. Before we dive into any actual numbers, let's lock in this shift rule so you never move your decimal the wrong way under pressure. Got a positive exponent? You're moving the decimal point to the right. Negative exponent? You're moving it to the left. Take a mental snapshot of this right now. Positive means right, negative means left. Simple as that. Part 3, moving right, positive exponents. Let's jump into our first practice example, where we tackle a negative mantissa paired with a positive exponent. In this setup from our source material, our exponent has been calculated as 3. Since it's a positive 3, our shift rule says we're moving right. Our source points out a really neat trick here. Because the original binary number was already shifted left to become normalized, our conversion process actually means we're moving it back by taking 3 hops to the right. Let's see how this actually works out when we apply our cheat sheet. The original mantissa had a leading 1. So we applied 2's complement, flipping the bits and adding 1. That makes our starting binary point 0.01101, followed by a bunch of trailing zeros. Next, we physically shift that decimal point 3 places to the right. It literally hops past the 0, past the 1, and past the next 1. So our new binary layout is 0011.010000. Now check out how easily we can decode this value. Just split the binary at the new decimal point. The whole number part on the left is 0011. In standard binary, that's just a 1 and a 2, which equals 3. Now look at the fractional part on the right, 0.01. The first spot after the decimal is a half, the second spot is a quarter. So we've got a quarter, or 0.25. Put them together, and the fractions add up perfectly to a total combined value of 3.25. But hold on. Put down your pencil, do not circle that answer just yet. We've got a red alert. Remember our very first rule? The original binary number we started with had a leading 1. That means it was a negative number from the very beginning. The two's complement process just helped us find its absolute value. You absolutely must remember to manually apply that negative sign to your final results, making the true answer minus 3.25. Part 4, moving left negative exponents. We've totally mastered the right shift, so let's walk straight into an ambush and see what happens with a negative exponent. Take a really close look at this second example from our sources. The mantissa is 101000, and the exponent is 1110. Do you spot the trap? Both of these numbers start with a leading 1. That means both the mantissa and the exponent are negative, and we've got to convert both of them using our two-step cheat sheet. We always handle the exponent first, so we know our shift direction. We apply our 2's complement steps to the exponent, flipping the bits of 1110 and adding 1. That leaves us with 0010. In standard binary, that's a decimary value of 2. But because of that original leading 1, we know it's actually a minus 2. Our exponent is negative 2.
Next up, we do the exact same conversion on the mantissa. We flip the bits and add 1 to the original 101000, getting 011000. Right here, our source highlights a supercritical step. We drop in an imaginary decimal point right after that first 0. So our new baseline is 0.11000.
Since our decoded exponent is -2, let's recall that rule table. Negative means we hop to the left. We grab that imaginary decimal point and shift it left twice. And since we run out of numbers, we just pad the left side with a couple of zeros. Our new correctly shifted binary fraction becomes 0.0011.
Now we just decode the new fraction. The positions go half, quarter, eighth, and 16th. Our ones are sitting perfectly in the 1/8 and 1/16 positions. Do a little basic math, add 1/8 and 1/16. Convert 1/8 to 2/16, add it up, and we get a nice clean 3/16. Oh, and as a quick mental practice example, if your exponent happened to be 0, you wouldn't shift at all. You just apply the negative sign and decode the fractions right where they sit.
Part 5. Common exam pitfalls. You've done all the hard work.
You successfully flipped the bits, added the ones, shifted the decimal, and even did the fraction math. But before we wrap, we have to talk about the final hurdle where so many students tragically lose their marks. The instructor in our source material specifically warns that we need to remember to put the minus value, which is really easy to forget this. And it's so true. Under the high pressure of a timed exam, you feel this huge sense of relief after solving those binary fractions, and you just want to jot down the answer and move on.
Don't fall for it. You have to look back at that original mantissa. It had a leading 1. So you must visually slap that massive minus sign back onto your final fraction. Your hard-earned 3/16 absolutely must become -3/16. Honestly, that single stroke of your pen is very often the difference between passing and failing these questions. As you review this explainer and build out your own computer science study guide, I wanted to make a habit of asking yourself this final, grade-saving question before moving to the next problem. You've done the shifts, you've done the math, but did you remember the final negative sign? Keep that front and center, lean on your 2's complement cheat sheet, and you're going to absolutely crush these conversions. But here's a thought to leave you with. What actually happens if you shift your decimals so far that you completely run out of bits? Does the whole computer crash, or is there some hidden failsafe? Well, that is a mystery we will solve in our next explainer.